Thursday, April 13th, 2023. Yet another day of reading about the path integral. The line integral began when it was discussed, the line integral and the challenges and difficulties of establishing the emergence of this measure of the length of the emergence of the integer lattice, which we usually set down as defined, because how can you start numbers without having a measure and without having 1.0 and without having thus the integer lattice? It's talked about then, what we get into then when we otherwise have this theory of a continuum, and continuum theory, how it's possible to arrive at these continuum mechanics that arrive at what makes tractable after it's fungible, after it's sensible, after it's intuitive and of its own nature, natural philosophy, physics, a course which is already set out for us, is getting into this talk of the path integral. And particularly in reading this book, Path Integrals and Quantum Processes, much as was read up after something like Descartes' the Method and these notions of the university mathematics texts of a usual curriculum provided to everybody after a usual primary and secondary curriculum that includes geometry, algebra, trigonometry, more algebra, more geometry, more trigonometry, pre-calculus and calculus it's called math. After, the primary education, which involves arithmetic and inequalities and, number sense and shape sense and geometry and math. Then from reading this nonlinear electromechanical effects and applications by Morgan, a lot was brought in as this book from World Scientific really helped to bring together some of the notions what are in the field as about the theory of potentials and how that harmonic theory is attaining to this theory of some potentials. And it was pointed out the other day that the differential topology and quantum field theory there, Nash's book, helps introduce the pseudo-differential, which is this degenerate, this deconstructive effort for then the reconstructive, to help arrive at what are the well-founded and valid, formal and rigorous, unambiguous and fruitful notions of the tractability after this sensibility of the fungibility of things, the methods that we can so arrive at how to mathematically frame these processes that are continuous processes, and how we can arrive at then in these infinite limits that they're complete, that induction is complete. And so there's talk about Zeno and Zeno's paradoxes. Isn't it a paradox for there to be a paradox? What if there's none? What if that's not a paradox? It's a paradox. It's none. That then there's so arrived at how these things again arise, and here there's a pretty specific denotation of the integers as at once whole and decomposable. So that it's possible to look at why you can have an object that models arithmetic of the addition and an object that models arithmetic of the division, and that they kind of work on both sides, that in the middle there's the integers, but on either side they're free. And thus it results that you can think about how it's possible then to result that this kind of thought experiment, the Gedanke of the setup, this Ansatz, that it's kind of neat in that sense, that it helps explain why the mathematics is discovered, and it's a Platonic reality, that it's fair, that it's fair, that it's non-judgmental and fair, in a sense that for the abstract and reason, it also allows us to then help understand how, when we need to relate algebras of words and formal methods on words, like the digital, how that relates to formal methods on the analog. That the digital and analog is a traditional dichotomy that models the discrete and continuous, the traditional dichotomy of cutting those two things apart, whereas at the same time they're one world of things. And that in our places reasonable thinking beings who can only really interchange things on a discrete level, on a digital level, in a sense, arrive at the ones that these are the analog things. That in our theory of the classical and linear, and then the potential and spherical or nonlinear, as what the surrounds is in the context, and how the context is the same as the inner context, and then we model these classical things both as outputs and arrivals, but also as a way and as they go, this dissipation and attenuation about the oscillation and restitution, that all these points together help establish why the dichotomy of the dialectic makes for the dialectic, so that then we can make for ourselves a simple enough logic that's free, also spare, that you can take it or leave it in our limited resources and means that as simple creatures on this green earth we have each. So it's to be reading the quantum processes, continuum processes, these that we even get into describing how the discretization of events and the whole particle theory is basically upended or turned over to help see it from the flip side, as it were, to build this context of the objective and subjective, the subjective and objective, that this ongoing dialectic helps to frame what are the utter fundamentals as fundamental utterances. That all these kinds of reversibilities in complementary terms, inverses, are generalized about how then we can talk about a unification in one sense, that there is a ground, a Grundgesetze, as Frege put it. That there's as well all the abstract realm of thought that is free for anyone to imagine the multiverse, or insofar as they otherwise in any manner so care to pose or frame any matters of reason or lack thereof, the reasoning of the lack of reason, or the truth about lies. These can all be kind of seen to soak down from this tower of rain, as it were, immobile celestial spheres in a cosmic clockworks, which is a pretty great thing. So anyways, as path integrals and quantum processes, we've been getting into chapter 3, which is evaluating the path integral. We got up a section about the free particle. So the free particle is basically a conceit, meaning it's concession to that this is the notion of our instantaneous in a continuous world, of the instanton and the soliton. The instanton being a particle, as of the ion, or fundamentally an active particle, and the instant of its placement, of its ansatz and its Gedanke, that is concession to that otherwise it's all the things that define it. It's its context. That the object in the universe is its context. And if, for example, the universe is just got a flickering light, like someone just constantly turns the light on and turns the light off, it works out the same, just because that's the most efficient way it could be in effect. The context is the complement in the universe, and it's the same as a thing. A thing is all the things that it is not. These are the ideas that help arrive at small closures in the way to approach any kind of logical judgment or observation. It is like so. So the free particle is at once that the particle defines its locale, it's local, and that it would be subject to what is its flux. So a free particle is in a sense like a gaseous model of things when there's also an infinite wind. So the supermodel, in a sense, has for light that it's like gaseous particles that float in an infinite wind. A very weak effect of these very weakest, smallest particles, this flux that makes for a global and a total flux gradient that's just a small constant. Now, if that sounds abstract, it's because it's the abstraction of the complement of the concrete, the discrete, the impulse, the measurable, and the fixed. The only constant is change. Geometry is motion. Truth is regular. In these manners, the dialectic arrives at a free particle, the article. All right then. In this section, the simplest possible system, that of a free point mass moving one-dimensionally, is analyzed using the path integral. So as before when we were talking about that, well, that satisfies the Heisenberg picture in the discrete case, and the continuous case, what we'll call it, is anything that then gets into details, differences. The Lagrangian is given by, and this section was read, Lagrangian of q dot q, the momentum operator's derivative with respect to time, q dot q equals 1/2 m q dot squared. This is familiar as that mv squared is as of the moment of what it turns about, what it would take to turn it about. This system can be analyzed very easily by operator techniques, since the associated Hamiltonian is given by h big P comma big Q equals big P squared over 2m. It's inverse proportional to mass given this outer product of P. Using completeness of the ket little p eigenstates, that it's a completely posed eigenvalue problem, and that the vectors add up, and so the triangle inequality is satisfied to establish and maintain the metric. And the form of the inner product, the transition element, can be written as, and this was read as z, the transition amplitude, often determined as of its root. This is where it says of the square and in our quadrature, and so it is as so y, this is so, that we define it in these terms, because then later we have to have it be about root mean square in terms. That the transition amplitude, which is the tendency for it to propagate, z of qb tb qa ta equals bracket of qb given the Hamiltonian of qa equals the integral from negative infinity to infinity, or the integral over r of in dp of the exponent times negative I p squared over 2 m Planck h bar tb minus ta, or the contributions of the pathline elements to the Gaussian integral of times these brackets, bracket qb given p and bracket p given qa, or those reversed, that makes what point outwards of it, what fills inwards of it, that those are integrated in the position, and then that equals integral over r of dp in dp of 1 over 2 pi Planck h bar. So inverse proportional those elements of piece, that the 2 by Planck h bar is that small constant, so its inverse would be large. When it's vanishing, that would grow of the exponent in terms of, here we result as having an additive term instead of a multiplicative term, as we've been just talking about decomposing arithmetic into addition and division, of negative I and this term in p squared over 2m Planck h bar, and the difference between tb and ta, tb minus ta, quantity, plus I p over Planck h bar qb minus qa, qb minus qa. So that's interesting that it basically makes an effect for the spectrum of the frequency and the time, that it very much reflects what goes on in terms of the Fourier analysis, and we have to talk about the spectrum. So after we talked about phase and the polarity, then we get into spectrum, and it's a pretty complicated issue because it helps to reflect what is the normal and the orthogonal in a curve. It continuously varies, and how it basically affects a change from one state to another that would have been orthogonal and polar to it through these transition of phase. So spectral operators. The spectral operators is quite an impressive field when you think about something that, like modern imaging satellites and remote sensing about the Earth, might have 38 spectral fields, 38 different bands of a sort, and how they have transforms of those in time and frequency, and it's quite a thing. That here, though, it's just that it's reflecting that the contributions in the path elements of this Gaussian integral are kind of having this oscillating about the plus and minus contributions in I, so they work up and down, that it's this complementary reciprocative action, this oscillating, and the recitative adds up these commutators have what results boxed down by the quadrature thanks to Gauss in these complex integrals, which deserves its own derivation and decomposition this way. So he says this is a Gaussian integral of the form 1.107, so that the final result is transition amplitude z qata qbtb equals quantity root of the square root of m over 2 pi I Planck h bar tb minus ta times quantity exponent I over Planck h bar and m qb minus qa quantity squared over t qb minus ta. So you have this difference in the momentum operators is squared, whereas the time contributions are rooted. And then this gets in this talk about the x squared plus minus 1, and gets in the talk about the y between 0 and 2 is a place that's centered at 1. And these ideas of symmetries that result how these things are boxed and halved and rotated and unboxed, that according to the triangle inequality, ... there's a trace, as it were. So that the final result is that form. Since the path integral form for the transition amplitude was derived from the operator formalism, it must also yield 3.4, which was just given. So looking back at where it says that it was Gaussian integral as a form was 1.107, which was given way back in the preliminaries. That was that the integral of over r of dx of e to the I alpha x squared plus minus I beta x equals root pi over I alpha exponent I beta squared over 4a. That's a complex version because the final extension of the formula is presented so far as to include the exponential a term that is linear in the variable of integration. So this gets back in this reformulation, the implicits, and why it's possible to do this variable substitution that is dangerous in the area to do this variable substitution, but arrives at it so follows out that then it's so contrived that the accumulators and the commutators add up to subtract away what grows out of these products, that then in this attenuating that the initial terms at least don't blow up, and they suffice to define a sequence that can be so derived as a series that has these terms. And thus this is given in a closed form after those assumptions and conditions in the derivation make it like to so. And then he says back on page 27 in under Gaussian integrals, it is straightforward to extend result ... to include a term linear in the x sub I. These are these ith positions, the infinitely many of them in the at the ith infinitesimal, given that it's related to 1.0 or 0 to 1.0. This is most easily accomplished by translating the xi that appears in ... by a constant beta I over 2, so that beta defines an n-dimensional vector, and then that gets into why there's the 1/2 in the terms. Why it works out that when we pour out all this stuff that would be continuous, that then we break it down, it reflects on Vitali's function and demonstration that it's possible to make infinitesimals from an infinitude or of what was split out of a unit and make 2. So before we ever get to Banach-Tarski's paradox, or that what's called ball doubling in doubling spaces, and then that can be torn down into 4 or 5 everywhere non-measurable, everywhere discontinuous regions that reassemble to each other and make such a thing. That's about the very nature of the points on the line, which are two-sided, or in the line, which are one-sided. So it makes it so that the analytical character kind of has so doubled from the very act of analysis. So anyway, it works out that dropping in this term 1/2, or why does 1/2 go in the equation, is also intuitively supported by the simple explanation I just gave. Back to section 3.1, it's described that the Gaussian integral was of the form so that the final result was given in that closed form, and it was derived from the operator formalism so that it yields it that way. In order to demonstrate that this is true, the action appearing in the path integral will be treated as a discrete sum. The equivalent version of 2.44 for this action gives transition amplitude equals integral from QA to QB in the root of the n over 2, which is the infinitude, the effectively infinite number. This quantity taken to that power of m over 2 pi I Planck h bar epsilon, this vanishing bit of it, of the product of each of the dqi's, and that times the exponent of which is this Gaussian integral's guide star, or its rotating pole, of I over Planck h bar of the sum of j from 0 to n minus 1, that infinitude of m over 2 epsilon qj plus I minus qj squared. So this transition amplitude of that being the equivalent of 2.44, what he refers on, this, if that's kind of its complement, and that they're assumed to meet in the middle, that they meet in the middle. So via a sandwiching, which is a sandwich is sandwich fillings between two slices of bread. So the sandwich theorems are that this is the lower and this is the upper, their difference goes to 0, they're sandwiched. And, or there's otherwise a course through the middle. It's also called Scylla and Charybdis, a rock in a hard place, that by staying the course, then it's to be defined that these two quantities together point in either way, in and out, that's so that, and again, any mistakes are my own, and it's to be assumed a generous reading, and you're free to be quite as so strict as you ever would care, that the 2.44 was the finite transition element z can finally be written as the product of the n infinitesimal elements, giving bracket of qb comma tb given qa comma ta equals the integral over r of d p naught times dot 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 d p n over 1, each of those over 2 pi Planck h bar, times the quantity dqi's, or it's rather the integral in all those dqi's, which should be 0 except in each of those little regions that they have, kind of a thing. So that this is the quantity is together, but it's all these piecewise pointwise the terms of this whole times, again, the exponent of I over Planck h bar sum j equals 0 to n minus I, epsilon Lagrangian of pj qj. So that's explaining how these quantities are balanced about what stakes them out and tents them out, that they fall in the middle. That this reading leads to why it's as simple as that in this continuous, in this discrete case of the continuous, that this is the arrival thus far in the development. And it's in terms of the free parameters, the mass of the particle and its motion according to its momentum, or rather the root thereof, and the change of that with respect to time. It's differential and reflects both the differentials of position and the differentials to rest. So the equivalent version of that is gives that it's like so, as was read. Then the author proceeds. Following Feynman and Hibbs, the intermediate integrations are performed in sequence. The first integration over Q sub 1 includes the Q naught and Q sub 2 factors. Singling out only the terms that are involved gives the integral of the dq1 in dq1 of the exponent of I over Planck h bar m over 2 epsilon quantity q2 minus q1 squared plus q1 minus qa squared equals the integral over r of dq1 exponent I over Planck h bar, and then a bigger quantity in these additive terms again, and one being the infinitesimal difference and the other one being the difference towards the endpoint of m over 4 epsilon. See, and then it's kind of squaring that term or doubling it. This is where it makes this so that, well, doubling or squaring kind of either way has to suffice. We need to keep it square for the quadrature. So triangle rule applies. Plus m over epsilon, that's lower order in that, but it's got then q1 minus 1/2 q2 minus 1/2 qa, all that quantity squared equals, and then for the closure of the form, as it were, the root altogether of the quantity pi I Planck h bar epsilon over m times the exponent, this quantity I over Planck h bar m over 4 epsilon q2 minus qa squared. That the little bit there has for where it arrives at this beginning and end, that it's still staked out that these are each of the terms. The first integration has produced another Gaussian integral. It is left as an exercise to show that the result of the nth integration has the form ... and he writes it out in terms of replacing the q1 minus qa with qn plus 1 minus qn. And otherwise there's some transformations about that in this box that is so built, each of these infinitesimal areas region. And then we talk about in the infinitesimally small, there are geometric mutations, whether a box is a circle or a circle is a box. It's a very natural setting to think of like the whole coordinate space as either a square or a circle. Here, it's pretty much usually in these terms. And we might, invoke the Yenri, or the calculus of circles, as an example of a kind of way of a thing that gets into that when we have like these one-sided points in a line and two-sided points on a line, and why Vitali's non-measurability is a doubling space, and thus we have a doubling space in our arithmetic formula that we have to fix, because in our arithmetic formula we're using a halving space, basically. That these are the kinds of things that get involved in continuum mechanics and adding things up. As a result, after the n minus 1 integrations have been performed and the identification Qn equals Qb is made, so when you make an identification, this is where that otherwise it would be like identifying it with the infinitesimals, this 0 to 1 to 0 to infinity. And so it's kind of a necessary tool and a pretty fundamental thing, and we call it Aristotle's continuum. Here we call it Vitali's example of the non-measurable space that's really a doubling space, exactly. And this kind of thing. And then, of course, then that demands apologetics for all foundations in set theory, because there's opinions and they're respected and explained. That identification Qn equals Qb is made. The path integral reduces to z of qa ta qb tb equals the exponent of I over Planck h bar m over qb minus qa squared over quantity 2n epsilon. This quantity is as a notation of a convention by itself, only so reflecting that these things are unbounded and effectively infinite, effectively infinitesimal, yet so framed as of about more than the raw differential, or still maintaining algebraically these other concerns of m over times the quantity of to the n over 2, or infinity over 2 here, or the semi-infinite, it's often called. The semi-infinite is what we talk about when we can't really talk about infinity, or infinity over 2, of the quantity m over 2 pi I Planck h bar epsilon times the quantity of the infinite product, just like the infinite sum is a big sigma, the infinite product is a big pi, then equals 1 to n minus 1 of the root of 2 pi I Planck h bar n epsilon over n plus 1 m. So in some of the other places where he's written, for example, the product of the infinitely many raw differentials, you could kind of write it in these terms. It's not so much the notation doesn't allow it as the convention doesn't make for it. Equals root of quantity m over 2 pi I Planck h bar big N epsilon times the exponent, or e to the I over Planck h bar m qb minus qa squared over 2n epsilon. So that m is the mass, which is the parameter. Also that the momentum operators and the momentum operator and timer is the parameters, are reflected in terms of this difference, these infinitesimal differences, or rather the endpoints, so the entire difference in the momentum, and is framed back down as from the momentum, a quantity in the root of m and e to the m. Or in quantity with regards to the mass, then, that would be of so, that otherwise it's also rationed on down to what would then be fundamentally extracting the real part of that as these transition amplitudes. Or is that's only what results when one of these amplitudes is in effect actualized or discretized. That's what must have happened, in the sense that that's the event in the probabilistic model that also is, in this context, the real wave function collapse of this superflux model. Recalling that n epsilon equals tb minus ta, the n goes to infinity limit reproduces the result 3.4, which was a transition amplitude of the final result of the transition elements of those Gaussian integrals of the 1.107, so that the path integral is identical in content to the operator formalism for this specific definition of action and measure. It preserves a metric. It's the triangle inequality is the rule. And the action is the definition of the action. The definition of the action. The action is some of these terms about the propagator. And it reflects a Lagrangian system that's parameterized by time. Each of these systems are axioms in the principle of least action. For this simple case, the path integral could scarcely be viewed as a calculational improvement over the operator formalism. However, some points of interest emerge from closer examination of the propagator. First, the Green's function for the time-dependent Schrödinger equation and the propagator are intimately related. The Green's function, g of x to x prime, t of t prime, for the one-dimensional form of Schrödinger's equation is defined as the function that satisfies, that's the operator approach, that the functions satisfy, of h, the Hamiltonian, of negative I Planck h bar, or for now just Planck, d over dx, comma x minus I Planck d over dt quantity, and that written with the raw differential, or its inverse respectively, of in dt and dx, so that the quantity must be so self-contained, and that here it's reflected in the Dirac delta, times g of xx prime tt prime equals I Planck delta x minus x prime delta t minus t prime. That the parameter to the delta function is its displacement, and it's using all sorts of convolutional methods, and all sorts of methods of transforms. About the spectral, which is also related to principal component analysis, as is to the gradient, that the spectral then is into the frequency and time domains, how the analytical character is so contrived. The Green's function is related to the propagator by g of xx prime tt prime equals theta t prime minus t z x prime t prime xt. So via this relation of the terms, and it makes a differential system. This is pretty good, because then it seems like it's possible to help reduce a lot of these terms into what can then make for that these become algebraic quantities, all else held algebraically quantified and qualified, that these are relating to the Green's function, which has many methods to approximate and compute the gradient descent of things, and is very well understood in terms of Green's and Stokes and Navier-Stokes, that I don't much know, but are very usual. That it's related to the propagator of the transition amplitudes this way, where theta, that he defines theta, where theta t prime minus t is the step function defined by 2.17. So the step function, we'd usually refer to Oliver Heaviside's step, just like when we refer to PAM Dirac's delta function, which is an infinite spike at 0 that has 0 width but has area 1, and as so modeled by functions, or as so resulting then that it's used like so, as after a limit of functions, analytical closure. That is, the step function 2.17 was, if it's not Heaviside step function, which is from the left 0 and from the right 1 as they meet at 0, a step of unit height. That is so, yeah. This is the same step function, Oliver Heaviside's step function. Not a classical function, but if you look at it from 45 degrees, it's perfectly a classical function. It's not a smooth function, but you can approximate it by smooth functions. That insofar as that then that builds, for example, when you're using it by summing coefficients in series in sine and cosine, or sine or cosine, that results that is particularly contrived thing that vanishes on the left and arrives on the right. Thus, it's indicated on the right and not on the left. It's boundary. And its analytical character on either side is so indicated as an indicator. So, relation 3.9, that was the previous given one in the raw differentials of x and t is about the delta of differences x and t. That I have to consider my reading of t prime, what it is. It's for the Schrodinger equation. That the step function is so defined, relation 3.9 can be readily demonstrated by using 2.19 and the definition of the propagator 2.30. The action of the time derivative gives I Planck d over dt of g, this Green's function, of x prime t prime equals negative I Planck delta t prime minus t z x prime t prime xt plus theta t prime minus t of bracket x given Hamiltonian I Hamiltonian t prime minus t over Planck given x prime. From the fact that z, the transition amplitude, x prime t xt equals bracket x given x prime equals delta x minus x prime, that it so results that inside these all the forms are closed. So what results makes it so? Relation 3.9 is immediately obtained. So in a sense that's saying, well, after you put it in and out of green, you get the same thing, so at least it wasn't broken. But at the same time, it's kind of starting with what you were meant to arrive at. So there's particulars about all else holding consistent, all else holding so, in this reformulation, that it's not so necessarily that that blindly of the terms, you couldn't arrive at that via any kind of algebraic manipulation. But just here it says select so that after it's come in and out of the terms, that they happen to be defined by separate means, that they box back up, is then expressing tractability in those means, fungibility in those means, thus that results, given time, there's tractability in those means. The fungibility is essential for tractability, except insofar here is that the tractability is built up in a quantity so as to arrive at that there must be the fungibility, this meeting in the middle, this sandwich. The second point is the role of the classical action in the overall result. The classical equation of motion q dot dot equals 0, uniform motion, is trivial to solve for the boundary conditions that QTA equals QA and QTB equals QB. This is the discrete case, the classical case, the vacuous trivial case that must add up because it's classical in the middle. And indeed, that's the whole point of this theory of some potentials and these kinds of things, is to arrive at classical from the superclassical. But anyways, here, that's not so much relevant, is that this formalism is that the classical action in the overall result is trivial, and then it follows that the classical trajectory, noted QCT of this, the momentum operator, QCT is given by QCT equals QA plus QB minus QA over quantity TB minus TA times quantity T minus TA. That it's evolved, and as it goes to T, that these differences are as in with respect to times prior to T, that arrive at so that QCT is given the initial state plus the contributions in the classical action in the differences as of a linear, that it works out this way. This fundamental humble ratio falls out, at least that these all add up, which would necessarily be so, that otherwise it would have to be figured out why that was not so. It is straightforward to show that the value of the action for the classical trajectory is given by S, the classical action, is the integral from TA to TB of in dt of 1/2 mq dot c squared equals in m 1/2 of m times quantity qb minus qa squared over tb minus ta. That it's a linear relation. By comparing this result to 3.4, it is apparent that the argument of the exponential appearing in the propagator is given precisely by I over Planck times the value of the action along the classical trajectory. The argument is z, and is given precisely. In section 3.3, this will be shown to be a general feature of all quadratic actions. So that gets up and that makes for up and above in the operator calculus why it's possible to then work up something like Feynman diagrams can be drawn and make sensible and fungible in that higher level just by the accords of the rules of drawing the diagrams, because these sorts of things are held up. And then particularly about the quadratic and the Cauchy-Schwarz inequality, the triangle rule and triangle inequality, and all this stuff that goes into the Gaussian and complex analysis and the product of vectors and the Gaussian integral in terms of this Jordan measure about this Dirichlet setup, that all these things are brought on back down in terms of these overall propensities of the classical action in the discrete case. And then it would probably be then these diagrams are meant to be the same things usually when we draw them with regards to whether it's the discrete or the continuous case. And so we can figure out when things are in a particularly contrived configuration of experiment that they line up because it should be classical, that Heisenberg has uncertainty, but he arrives on time given the proper dimensions. Then it is to make so for then whether and how these other continuous cases are derived and defined, when they would be different. All right, so then he gets in, that's the section 3.1, and he gets into what is this groundwork that goes into having, for this test particle, a free or test particle, just one, the object under analysis of it, of an atomic, dimensionless body. That's why it becomes the particle zoo, because everything's a particle in the particle zoo, and maybe their masses and energies vary and their momentums and this and that, but everything else is, as of the waves above them are mechanics, they're defined this way. That's pretty interesting. So again, and that would make it so that some later stuff can still all be written in this classical way. Well, really, it has a non-classical or this formalisms under it that have to be maintained with regards to then that when the configuration of the experiment is bent, that these symmetries flex and don't break. That there's no symmetry breaking, there's symmetry flex. All right, well, that's some reading of the path integral for today. And let's see, did I study this before? I took physics before in a school. It was a good physics class. We had relativity and we had the tensorial notation and this and that. I already studied that. Einstein's summation convention and this and that, We talked about Broncat and the Hamiltonian and this and that. And it was introduced things like modeling Dirac's delta as a limit of functions. In fact, it was kind of presented more there first in the physics side, before it came up in the mathematics side, which is about the use in the solution of differential equations after methods of transformations and transforms, and the spectral analysis, which results as after systems or orthogonal functions like sine and cosine or any other pair of orthogonal functions defines a transform, and then that all the applications properties of about the operator calculus can be so applied neatly that the physics course then addressed that a lot of these formalisms are about same in terms of their application as about what they convey, and then also the centrality of for the quadrature, and if not so much in this terms of the boxing of things and the halving of things and the squaring and things and about the normalization and standardization of variables, which mostly came out in its development in a probability theory course, that the Cauchy-Schwarz or triangle inequality is placed centrally as the rule that establishes that there's flex without breaking. Well, all right then. Let's see what the Feynman has to say here. Page 147. Actually, these are interesting books because these Feynman lectures, they don't really have page numbers of all the pages, but each section has its own little page numbering. So these may have been provided in terms of like many books. So each one of these workbooks of a sort has like 10 or 20 things or books. And so if I was interested to see what's in 17-7, 17-3, 17-8. So okay, so 17-5 is the 4-vector algebra. And so the 4-vector algebra is then what happens when in an orthonormal vector space that the 4-vector is these splittings. It's like, well, there's a planar curve and there's a tangent. And so at that tangent, the tangent is split. So these and as of either of these sides reflecting about that would add up to these commutators and the addition formula, which result that according to the derivations of these Jordan measure line elements of the path integral and such things. That's what 17.5 is about, 4-vector algebra. If there's an equation among 4 vectors, then the equation is true for each component. For example, if the law of conservation of 3-vector momentum is to be true in particle collisions, i.e. if the sum of the momenta for a large number of interacting or colliding particles is to be a constant, then that must mean, it must mean that the sums of all momenta in the x direction, in the y direction, and in the z direction for all the particles must each be constant. This law alone would be impossible in relativity because it is incomplete. It's like talking about only 2 of the components of a 3-vector. Well, that's about like the partial is the particular, and the singular is the point, and the general is this complete, but then the general is its outer context. And that these 4 vectors are as well reflected in theories like that of Elie Cartan's reflections and rotations, vectors, and symmetrical bilinear products. So that's what he's talking about. And it is incomplete because if we rotate the axes, we mix the various components, so we must include all 3 components in our law. And so this is similar as we were talking about earlier in the application of the manipulation of the formulas, in the formulas and the formulas, and the quantities and the quantities and the quantities, that it requires these winding arguments, as it were, the spiral or winding, to sketch out that there's context that maintains these orthogonalities in the rotation. So this just gets back to the earlier comment in this talk about the orthogonalities in the rotation. So Feynman here in 17.5 of volume 1 is explaining in 4-vector algebra that this algebra is like so, and where it's incomplete for relativity's sake, and why it must be and must mean it so for these things. It is incomplete because if we rotate the axes, we mix the various components, so we must include all 3 components in our law. Thus, in relativity, we must complete the law of conservation of momentum by extending it to include the time component. This is absolutely necessary, emphasis the authors, to go with the other 3, or there cannot be relativistic invariance. This is this preservation of symmetries, preservation of conservations. Here it's in our context, we're talking about a continuity law. And that the continuity singularity is besides the asymptote for singularity theory, it's a spiral space-filling curve from the origin, which would have kind of these properties already established for itself. They're trivial. But not in our Cartesian, and where it's only tractable and fungible from our orthogonal vector space. Applied. This is absolutely necessary, or there cannot be relativistic invariance. The conservation of energy, emphasis to authors, is the fourth equation which goes with the conservation of momentum to make a valid four-vector relationship in the geometry of space and time. So this is reflecting that this is the potential. This is where all the rest of the contributions or terms in the potential live, because the continuity laws, or as for aminoid and asymmetry implies a conservation law and invariant theory, that this is so. And Feynman is helping us understand that these sorts of brackets help define his intuition, which was so critical to his developments, that he was able to arrive at these means that make it so that quantum mechanics is in effect. For it is of a continuum mechanics, and that these symmetry and conservation laws are continuity laws. And when I say that with quite a strong accent on the continuity, they're continuity laws. A four-vector relationship in the geometry of space and time. Thus, the law of conservation of energy and momentum in four-dimensional notation is sum for particles in of p mu equals sum particles out p mu. Or in a slightly different notation, sum of I of p of I mu equals sum of j p of j mu. Where I equals 1, 2, dot, dot, dot refers to the particles going into the collision, j equals 1, 2, dot, dot, dot refers to the particles coming out of the collision, and mu equals x, y, z, or t. You say, in which axes it makes no difference. The law is true for each component using any axes. So this is helping to reflect that particles in, particles out is in this wave action. And he's helping express that overall in the system that there are closed systems in physics which always maintain all their energy inside, and there are open systems in physics, but physics is an open system. So all these conservation laws, eventually have to balance everything, and so he's expressing that this is the balance. What goes in comes out. In terms of energy, over the boundary. He doesn't say how big the boundary is or how it's oriented. It's just expressing that this is a continuity law. In vector analysis, we discussed one other thing, the dot product of two vectors. Here, similarly, we've been talking about the root in the Gaussian, which is sometimes the same thing as a half. For when a quantity is a half its square root. In vector analysis, we discussed one other thing, the dot product of two vectors. Let us now consider the corresponding thing in space-time. In ordinary rotation, we discovered there was an unchanged quantity, x squared plus y squared plus z squared. In four dimensions, we find the corresponding quantity is t squared minus x squared minus y squared minus z squared, or rather t squared minus quantity x squared plus y squared plus z squared. How can we write that? One way would be to write some kind of four-dimensional thing with a squared dot between, like a mu diamond dot bu. Here he's reflecting it this outer product of a sort, where you have things like direct sum and direct product, or like when it's encircled. Here, this is Feynman's diamond notation for the dot product, the inner product as of the outer product. One of the notations which is actually used is this sum in mu prime of a mu equals a sub t squared minus quantity a sub x squared plus a sub y squared plus a sub z squared. The prime on sigma means that the first term, the time term, is positive, but the other three terms have minus signs. This quantity then will be the same in any coordinate system, and we may call it the square of the length of the 4 vector. For instance, what is the square of the length of the 4 vector of momentum in a single particle? This will be equal to pt squared minus px plus py plus bz each squared quantity. Or in other words, e squared minus p squared, because we know that p sub t is e. And this is all in the fact that the potential and the actual energy also meet in the model. And then about 1/2 of that ends up being the classical term. It's very involved. In particular, it must be the same for a coordinate system which is moving right along with the particle in which the particle is standing still. If the particle is standing still, it would have no momentum. So in that coordinate system, it is purely its energy, which is the same as its rest mass. And this reflects back on the idea of the derivatives of displacement vis-a-vis what is rest. And for relativity, what is the frame? So in that coordinate system, it is purely its energy, which is the same as its rest mass. Thus, e squared minus p squared equals m naught squared. It's classical action, comes on down. Take the root of that, must be half. So we see that the square of the length of the vector of the form vector momentum is equal to m naught, m0 squared. From the square of a vector, we can go on to invent the dot product, or the product which is a scalar. This gets into the why the dot product is something that's computable, and how, as he puts it, it is the same in all coordinate systems. Not that it's coordinate free, but it's just the same. Well, there is no 17.7, but that's that's much as 17.5. Finally, we shall mention certain things whose rest mass m naught is 0. A photon of light, for example. A photon is like a particle in that it carries an energy and a momentum. The energy of a photon is a certain constant called Planck's constant times the frequency of the photon. E equals h, not h bar, Planck's h bar, but here it's just h times v, velocity. Such a photon also carries a momentum, and the momentum of a photon, or of any other particle, in fact, is h divided by the wavelength, p over h over gamma, lambda. Lambda. But for a photon, there's a definite relationship between the frequency and wavelength. V equals c over lambda. So here's expression that the photon is the light-like quantity, and so we have our space-like and our time-like axes and curves, and then light-like quantities. And then it's interesting because he's just defining it in terms of this bound. That is c, the velocity of light in deep space in a vacuum far distant from any massy bodies and undisturbed by any gravitational waves. As about that's related to Planck's constant, as from what's measured from electron physics, as from what's assumed then about light's behavior as a massless particle in this supergas model of flux, infinite wind, as it was put, or the very weakest force of the very more weak particles, their flux. That a photon has momentum. It's about whether momentum is a conserved quantity. It's not. It's an open system. But it is an invariant in usual classical action, which is fine. Thus, we see immediately that the energy of a photon must be the momentum times c. Or if c equals 1, or the natural units, the energy and momentum are equal. That is to say, the rest mass is 0. So this is when the natural units, placing c equal to 1, is essentially from the framing down of that, making that it's infinity, and so its reciprocal is infinitesimal. Well, that's about it for today. Imagine what we might arrive at later is some more of the same, where sometimes less is more, and sometimes it's just half. And so, if there's one, key thing about that is Vitali and his decomposition of a continuous line segment into discrete points. He reassembled those. He's made a doubling space, and so Vitali's non-measurable set isn't some length between 1 and 3, it's 2. And so in this manner, we can arrive at what's a very critical rule about the discrete and the continuous, that when you divide something down to the discrete from the continuous, it's basically got twice as much length. And so that's a particular thing. And when I say revitalization of measure theory, that's for doubling spaces, that the line integral, the line continuity has points in a line, and they only have one side, and so they add up to 1. Now, if you divide it down to those and split them up, whether it's complete order fields or for the signal continuity, that makes 2, or 1 apiece for then what is the doubling space. Then in these halving spaces, why it's so. It's a very fine comb. All right then, hey, have a great day.